66 million years ago, an asteroid roughly 12 kilometers across, wider than the entire length of Manhattan Island, struck the shallow coastal waters off what is now Mexico's Yucatan Peninsula, traveling at approximately 72,000 kilometers per hour, fast enough to cross the continental United States in about 3.5 minutes. The energy released in that single second of contact exceeded 10 billion Hiroshima bombs, detonating simultaneously. To put that number in proportion, it represents more energy than every nuclear weapon ever built by every nation on Earth, fired at once multiplied by 1,000. Within 3 minutes, a wall of superheated rock and gas had sterilized every living thing within 500 kilometers of the impact site, an area roughly the size of Alaska. Within hours, the sky across entire continents was on fire. Within weeks, the planet was dark. Within a few thousand years, 3 out of every 4 species on Earth had been erased from the geological record. Every non-avian dinosaur that had ruled the planet for 165 million years, every flying pterosaur, every mosasaur and plesiosaur that had patrolled the oceans since before the first flower ever bloomed, every ammonite, a group of shelled marine animals that had survived for over 300 million years through multiple previous mass extinctions, eliminated permanently. On land, virtually no animal weighing more than roughly 25 kilograms, about the weight of a medium-sized dog, left any descendants. But something lived. Small, quiet, burrowing creatures the size of a modern rat, hiding beneath the scorched surface in tunnels barely wider than a human fist, chewing on beetle larvae and seeds while the forest above them turned to charcoal. And from those creatures, from animals you could hold in one hand, came every mammal alive on Earth today. Every blue whale, the largest animal that has ever existed. Every elephant, every wolf, every bat, every dolphin, every primate. You. So how did a planet built around the most dominant group of large animals in geological history become a planet run by creatures that had spent 160 million years hiding in holes? The answer took paleontologists decades to assemble, and the most critical evidence was locked inside a hillside near Colorado Springs that nobody had examined for 66 million years. It was the final age of the Cretaceous, and the planet looked nothing like the world you know. The continents were still drifting toward their modern positions. India was a solitary island, racing north through open ocean on a collision course with Asia that would eventually push up the Himalayas. Australia was still fused to Antarctica. The Atlantic Ocean was barely half its current width, and a shallow seaway split North America in two, running from the Gulf of Mexico all the way to the Arctic Ocean. Across every landmass, from pole to pole, dinosaurs dominated the landscape in a way that is genuinely difficult to overstate. Tyrannosaurus rex stood 4 meters tall at the hip and weighed more than 9 metric tons, heavier than an adult African elephant. Triceratops herds moved through forests of magnolia, cypress, and fern, each individual massing as much as a modern pickup truck. In the skies, Quetzalcoatlus, the largest flying animal ever documented in the fossil record, cruised on a wingspan stretching nearly 11 meters from wingtip to wingtip, wider than a single-engine Cessna. The oceans belonged to mosasaurs, marine reptiles reaching 15 meters in length, longer than a city bus, armed with rows of teeth designed for crushing the shells of ammonites the size of truck tires. Mammals existed. They had been around for over 150 million years at that point, first appearing in the fossil record during the late Triassic, roughly the same geological period that produced the earliest dinosaurs. But they occupied a fundamentally different position in the ecosystem. Gregory Wilson Mantilla, a paleontologist at the University of Washington who has spent more than 2 decades studying the mammalian fossil record of the final Cretaceous, has documented that the vast majority of mammals alive in that era weighed less than 1 kilogram. Many weighed less than 100 grams, about the weight of a bar of soap. The largest known Cretaceous mammal in North America, a species called Didelphodon, was roughly the size of a modern opossum and weighed perhaps 5 kilograms. It was the exception. Nearly everything else was tiny. These animals were insectivores, seed-eaters, and occasional scavengers. Based on the structure of their inner ears and the relative size of their eye sockets, many were nocturnal, emerging only after dark when the great daytime predators were sleeping. And they were burrowers. Their limb bones and claw morphology show clear adaptations for digging. Their fossils turn up in ancient tunnel systems, in sediment compressed between tree roots, in tight crevices between rocks, where nothing larger could follow. For over 150 million years, this was the arrangement. Dinosaurs owned the day, the canopy, the open ground, and the oceans. Mammals owned the margins, the dark hours, the underground. Being small and hidden looked like nothing more than a strategy for not going extinct. Not winning, just persisting. This arrangement was about to become the most consequential survival advantage in the history of complex life on Earth. But in the final centuries of the Cretaceous, there was no way to know that, because what was approaching had not happened on this scale in 180 million years. On what geologists now date to approximately 66.043 million years ago, a body of rock and metal, roughly the diameter of San Francisco, entered Earth's atmosphere at an angle of about 60 degrees and struck the seabed near the northern coast of the Yucatan Peninsula. The impactor punched through 30 meters of ocean water, roughly the height of a 10-story building, and then through 3 kilometers of limestone and sedimentary rock, more than 3 times the height of the world's tallest skyscraper, in less than a second. The kinetic energy converted to thermal energy instantaneously, vaporizing the asteroid itself, the seabed beneath it, and a column of water, rock, and atmosphere that climbed nearly to the edge of space. The crater it left behind, now called Chicxulub, after a small nearby Maya village, measures 180 kilometers from rim to rim. If you place that crater over central London, its edge would reach past the coast of France. If you placed it over New York, it would stretch from Manhattan to Philadelphia. Sean Gulick, a geophysicist at the University of Texas at Austin who co-led the 2016 International Ocean Discovery Program expedition to drill into the Chicxulub crater's peak ring, recovered core samples that reshaped the scientific understanding of why this specific impact was so lethal. The seabed at the impact site was rich in sulfur-bearing minerals, particularly gypsum and anhydrite. When the asteroid vaporized those rocks, it launched hundreds of billions of tons of sulfur dioxide aerosols into the stratosphere, where they spread across the globe and reflected incoming sunlight back into space. The result was a climate disruption far more severe than the asteroid's physical energy alone could have caused. Gulick and his colleague Joanna Morgan of Imperial College London published their analysis of the drilling cores in 2020 in the Proceedings of the National Academy of Sciences. Their conclusion was blunt. The geographic location of the impact was the critical variable. An asteroid of the same size striking deep ocean basalt, which contains far less sulfur, would have caused catastrophic regional damage, but might not have triggered a global mass extinction. The sulfur amplified the climate disruption beyond what the biosphere could absorb. The worst asteroid in 180 million years struck the worst possible geology on the planet. And the asteroid did not strike a healthy planet. By the time the Chicxulub impactor arrived, massive volcanic eruptions had already been underway in what is now western India for hundreds of thousands of years. The Deccan Traps, one of the largest flood basalt provinces on Earth, covering an area roughly half the size of modern India, had been pumping sulfur dioxide and carbon dioxide into the atmosphere at rates that were already straining global ecosystems. Some researchers, including Gerda Keller of Princeton University, have argued that the volcanism was the primary driver of the extinction, with the asteroid serving as a final blow to a biosphere already in crisis. The mainstream view, supported by the precise timing of the extinction relative to the impact layer and boundary clays worldwide, holds that the asteroid was the dominant cause. But the debate is not fully settled, and the evidence suggests that the combination of both events made the extinction significantly worse than either would have been alone. But the sulfur and the volcanism were only part of the killing sequence, and they were not even the fastest mechanisms. Robert De Palma, a paleontologist working in the Hell Creek Formation of North Dakota, published findings in 2019 describing what happened in the first hours after the Chicxulub impact. His site, called Tanis, sits more than 3,000 kilometers from the crater, roughly the distance from New York to Denver. And yet the deposit De Palma uncovered there records the violence of the impact in extraordinary detail. Fish, turtles, ammonites, tree trunks, and fragments of marine organisms were tangled together in a chaotic mass of sediment, embedded with tiny glass spherules called tektites. These spherules are droplets of molten rock blasted into the upper atmosphere by the impact, briefly launched beyond the atmosphere entirely, then rained back down across the planet within 1 to 3 hours of the collision. The tektites were still hot when they landed. Some were found lodged in the gills of fossilized paddlefish that had been alive, breathing, swimming, when the glass fell from the sky. Doug Robertson of the University of Colorado published a 2004 paper in the Bulletin of the Geological Society of America calculating the thermal consequences of this ejecta re-entry. His models showed that the mass return of ballistic debris heated the upper atmosphere to oven-like temperatures for a period lasting roughly 20 minutes to 2 hours, depending on distance from the impact site. Any exposed animal caught on the surface during that window would have received lethal heat exposure within minutes. Simultaneously, the impact generated tsunamis in the Gulf of Mexico estimated at over 100 meters in height, taller than the Statue of Liberty from base to torch. These waves propagated across the Atlantic and into the Pacific, reaching coastlines thousands of kilometers from the impact site. At Tanis, Seychelles waves generated by the seismic shaking arrived before the tektites fell, hurling marine organisms from the western interior seaway inland and mixing ocean creatures with freshwater fish and terrestrial debris in a single catastrophic flood. Then came the fires. Soot records preserved in KPG boundary sediments from sites on every continent contain elevated levels of polycyclic aromatic hydrocarbons, chemical markers of widespread combustion. The evidence suggests that more than 70% of the world's forests may have burned within weeks of impact. These were not brush fires or regional wildfires. They were continental-scale conflagrations so vast that the smoke joined the dust and sulfur already in the stratosphere, thickening the atmospheric blanket that was blocking sunlight from reaching the surface below. If you are watching this, and the scale of this event is starting to register, subscribe now. I cover deep prehistory every single week, and the next video goes into an event that came even closer to ending everything. And then the darkness came down like a curtain across the entire planet. Julia Brugger, a climate scientist at the Potsdam Institute for Climate Impact Research in Germany, published a simulation in 2017 using a fully coupled ocean-atmosphere general circulation model to reconstruct the post-impact climate. Her results showed that global average surface temperatures dropped by as much as 26 degrees Celsius in the months following the impact, a swing roughly equivalent to going from a warm summer afternoon in Madrid to a winter night above the Arctic Circle. Ocean surface temperatures fell by approximately 11 degrees. The tropics, warm and humid for tens of millions of years, experienced near-freezing conditions for the first time since the Carboniferous period. Without sunlight, photosynthesis stopped across the planet, and when photosynthesis stopped, the entire food web built upon it collapsed from the bottom up. This is the detail that changes the math entirely. The asteroid did not kill most of its victims directly. The fireball, the thermal pulse, and the tsunamis killed organisms within a few thousand kilometers of the impact and along exposed coastlines worldwide. That was devastating, but it was geographically limited. The overwhelming majority of species that went extinct during the KPG event died of starvation. They starved because the base of the food chain, the photosynthetic organisms that convert sunlight into the energy that feeds everything else, went dormant or died when the sun disappeared behind a curtain of dust, sulfur, and soot that took between 18 months and 2 full years to clear. Plants stopped growing. Herbivores that depended on living vegetation could not eat. Carnivores that depended on those herbivores could not eat. In the oceans, phytoplankton populations crashed, and the zooplankton, fish, and marine reptiles that relied on them collapsed in sequence. The food web was severed at its base, on land and at sea, simultaneously, across the entire planet. And the organisms most vulnerable to this severance were the ones that needed the most food to stay alive. Think about the caloric demands of a 9-ton Tyrannosaurus rex for a moment. Biomechanical estimates from John Hutchinson at the Royal Veterinary College in London suggest an adult T-Rex required roughly 40,000 to 50,000 calories per day to maintain its body mass, roughly equivalent to eating 80 large steaks every 24 hours. In a world where vegetation had stopped producing new growth and herbivore populations were collapsing week by week, a predator with those caloric requirements could not have survived more than a few weeks without prey. Even the herbivores themselves were doomed. A 4-ton Triceratops needed to consume enormous quantities of plant matter daily to sustain itself. When the ferns and conifers stopped growing and nothing replaced them, there was simply nothing left to eat at the scale those animals required. Now compare that to a shrew-sized mammal weighing 100 grams, about the weight of a deck of playing cards. A mammal that size needs roughly 10 to 15 calories per day. It can meet that requirement with a few beetle larvae, a handful of seeds cached underground, or a scavenged fragment of decomposing material. In the devastated post-impact landscape, those food sources were still present. Beetle larvae persisted in dead wood. Ants maintained colonies underground. Seeds lay dormant in the soil, waiting for conditions to improve. Fungi thrived on the dead organic matter that now covered the ground in quantities that no living forest had ever produced. The food sources that sustained small mammals were exactly the food sources that persisted through the collapse of photosynthesis. That was not a coincidence. It was the product of over 150 million years of evolutionary pressure that had forced mammals into dietary niches that turned out to be the only ones capable of surviving an asteroid impact. Which of these details changes how you think about extinction? Drop your answer in the comments. The conversations in this community are consistently among the best on the platform, and I feature the strongest responses in future videos. The relationship between body size and extinction risk during the KPG event has been quantified with striking precision. Nick Longrich, a paleontologist at the University of Bath, published a 2016 study analyzing survival patterns of terrestrial vertebrates across the KPG boundary. His analysis confirmed what the fossil record had implied for decades. On land, virtually nothing weighing more than about 25 kilograms left descendants. The filter was consistent across continents, across taxonomic groups, and across dietary strategies. Herbivore, carnivore, omnivore, it did not matter. If the animal was large, it died. If it was small, it had a chance. The reason is rooted in a principle ecologists call metabolic scaling. Larger animals require more total energy in absolute terms, but the deeper vulnerability is systemic. A breeding population of large herbivores does not just need plants. It needs a vast, continuously productive landscape of plants, replaced seasonally, distributed across territory large enough to prevent overgrazing, sustained across dozens of generations. When that landscape went dark and stopped producing new growth, the carrying capacity for large-bodied animals dropped to functionally zero within months. Small animals operate under fundamentally different constraints. Their generation times are measured in weeks or months, not years or decades. A population of small mammals can double in a single breeding season. Their territories are measured in square meters, not square kilometers. And their dietary flexibility allowed them to switch between food sources as conditions changed, day by day, from insects to seeds to fungi to carrion, depending on what the ruined landscape offered. David Grossnickel, a paleontologist now at the Field Museum in Chicago, published research in 2019 examining the dental morphology of late Cretaceous mammals that survived the extinction versus those that did not. The results were clear. Survivors had generalist dentition, teeth capable of processing a wide range of food types including insects, seeds, fungi, and soft plant matter. Mammals with specialized teeth, the ones adapted for eating only fruit, or only tough vegetation, or only specific prey items, went extinct at higher rates even when they were small. Size was the primary filter. But among the small mammals, dietary flexibility was the secondary filter separating survivors from victims. And there was one more advantage the survivors shared, one that had nothing to do with metabolism or diet. They could disappear underground. The fossil record of late Cretaceous mammals is filled with species showing skeletal adaptations for burrowing. Robust forelimbs with pronounced muscle attachment sites. Curved, reinforced claws. Compact body plans optimized for moving through tight subterranean spaces. These animals did not simply forage on the surface and retreat below ground to sleep. Many of them lived underground. And in the hours and weeks following the Chicxulub impact, the underground was the only safe place on the planet. Robertson's thermal pulse calculations demonstrated that surface temperatures during the ejector re-entry phase would have been lethal to exposed animals within minutes across much of the globe. But soil is an extraordinary insulator. Even a few centimeters below the surface, ground temperature remains essentially stable regardless of what is happening in the air above. An animal sheltering in a burrow half a meter deep, roughly the length of your forearm during the thermal pulse, would have experienced almost no temperature change. The fire raging above, the superheated air, the raining glass, none of it would have penetrated the earth. When those animals emerged, days or weeks later, they found a world transformed beyond recognition. The forests they had known were gone, and the enormous predators they had spent their entire evolutionary history avoiding had vanished with them. The sky was choked with particulate matter, and the air carried the smell of sulfur and charcoal. But the ground was still there. And in that ground were the insects, the larvae, the seeds, and the roots that would sustain them through the months and years of darkness ahead. Daniel Field, a paleontologist at the University of Cambridge, reached a parallel conclusion when studying bird survival across the KPG boundary. Field published a paper in 2018 in Current Biology demonstrating that the lineages of birds that made it through the extinction were overwhelmingly ground-dwelling species. Tree-dwelling birds, which depended on intact forests for nesting, foraging, and shelter, went extinct when global deforestation destroyed their habitat within weeks of the impact. The ancestors of modern chickens, ducks, and ratites, the large flightless birds like ostriches and emus, survived because they could function on open ground, in devastated landscapes, without trees. And no, I am not making that up. The ancestors of every songbird, every eagle, and every parrot alive today trace back through the KPG bottleneck to ground-dwelling lineages that survived the aftermath. The birds that fill forest canopies today descend from birds that survived specifically because they did not need a canopy. The forests they now inhabit are forests that grew back after the ones their ancestors knew were destroyed. If the idea that every bird outside your window descends from a ground dweller that survived because the trees burned changes how you see the natural world, hit subscribe. This channel covers the deep past every week, and the next video connects to everything you have just heard. But the survival filter was not limited to mammals and birds. It extended across the entire animal kingdom, and the organisms that made it through reveal something that burrowing and ground-dwelling alone cannot explain. Crocodilians survived the KPG extinction. So did freshwater turtles. So did freshwater fish. The pattern was striking and for decades puzzling. How did cold-blooded reptiles that cannot burrow, cannot regulate their own body temperature, and cannot survive prolonged freezing make it through an event that killed every large warm-blooded dinosaur on the planet? The answer lies in the structure of freshwater food webs. Unlike terrestrial ecosystems, which depend on photosynthesis from living plants, and unlike open ocean ecosystems, which depend on photosynthesis from phytoplankton, freshwater ecosystems are heavily based on detritus. Dead organic matter, fallen leaves, decomposing wood, algal mats, and the invertebrates that feed on them form the base of the freshwater food chain. When photosynthesis collapsed globally, the detritus-based food webs in rivers, lakes, and swamps continued to function. There was plenty of dead organic material to sustain the organisms at the bottom of those chains, and the animals higher up, the turtles, the crocodilians, and the freshwater fish, continued to find food. Crocodilians also have extraordinarily low metabolic rates. A large crocodile can survive for over a year without eating a single meal. Its energy demands are a fraction of those of a similarly sized mammal or dinosaur. In the post-impact world, where food was scarce and temperatures were plummeting, having a metabolism that barely ticked over was an enormous advantage. The KPG extinction did not simply favor small animals. It favored animals with low energy demands, flexible diets, and access to food webs that did not depend on active, ongoing photosynthesis. The small burrowing mammals met those criteria. The ground-dwelling birds met those criteria. And the freshwater reptiles met those criteria through a completely different set of biological adaptations. The filter was the same. The solutions were different. And together they explain why the post-extinction world looked the way it did. Pay attention to this next detail, because it explains everything about how the modern world of mammals came to exist. The Hell Creek Formation stretches across Montana, North Dakota, South Dakota, and Wyoming. It is one of the most intensively studied geological formations on Earth because it straddles the KPG boundary, the thin clay layer marking the dividing line between the age of dinosaurs and the age of mammals. Below that clay, dinosaur fossils fill the rock. Above it, they vanish. The transition is abrupt and visible to the naked eye. You can stand on a hillside in eastern Montana, place your fingertip on the boundary clay, and know with certainty that everything below your finger inhabited a world ruled by dinosaurs, and everything above it inhabited a world where they no longer existed. Craig Scott, the Director of Preservation and Research at the Royal Tyrrell Museum in Alberta, has described the mammalian record in the Hell Creek Formation as a story told in fragments. Below the boundary, mammal fossils are present but rare compared to the dinosaur remains surrounding them: small jaws, isolated teeth, scattered limb bones. The mammals are there, but they are clearly marginal players in a dinosaur-dominated ecosystem. Above the boundary, within just centimeters of geological deposition representing perhaps a few thousand years, the picture shifts. Mammal fossils become more common, more anatomically diverse, and within a few meters of sediment, representing roughly 100,000 to 200,000 years of geological time, measurably larger. That pace of change is not normal. Under standard evolutionary conditions, significant increases in mammalian body size take millions of years. What the Hell Creek record shows is something far faster. An ecological vacuum created by the sudden removal of every large animal on the planet, and the small survivors rushing into that empty space at a speed that is, by geological standards, explosive. But the Hell Creek record has gaps. The sedimentary sequence above the KPG boundary is incomplete in many areas, interrupted by erosion and tectonic activity over the intervening 66 million years. The continuous, unbroken record that paleontologists needed to track the mammalian recovery century by century and millennium by millennium did not come from Montana. It came from an unremarkable hillside near Colorado Springs that nobody had thought to examine carefully. In 2016, Tyler Lyson, the curator of vertebrate paleontology at the Denver Museum of Nature and Science, began systematically surveying a set of eroded bluffs east of Colorado Springs at a locality called Corral Bluffs. Other paleontologists had visited the area before and found little of interest. The exposures looked unpromising. The rocks were drab, the terrain was nondescript, and the site lacked the dramatic bone beds that typically attract attention in Western paleontology. Lyson tried something different. Instead of scanning for bones weathering out of the surface, he began cracking open the rounded limestone concretions scattered across the hillside. Concretions form when minerals precipitate around a nucleus in the sediment, often a piece of organic material, such as a bone or shell, and inside those concretions, preserved in three-dimensional detail that surface-weathered fossils almost never achieve, were skulls. Hundreds of skulls. Mammal skulls, turtle shells, crocodilian remains, and plant fossils, all locked in a continuous stratigraphic section spanning the first 1 million years after the KPG extinction. No other site on Earth had produced anything comparable. Lyson and his team ultimately recovered more than 6,000 vertebrate fossils and 37,000 individual pollen grain samples from Corral Bluffs, building the most detailed and complete record of post-extinction recovery ever assembled anywhere in the world. The story those fossils told was revelatory, and it followed a sequence tied directly to the return of specific plant ecosystems. In the first 100,000 years after the impact, the mammals at Corral Bluffs were still small. The largest species recovered from this interval weighed roughly 6 kilograms, about the size of a raccoon. The vegetation in this period was dominated by ferns. Fern spores are among the first biological signals to appear above the KPG boundary worldwide, a phenomenon that paleontologists call the fern spike. Ferns are pioneer species, the first plants to colonize devastated landscapes before anything else can take root. And the mammals living among those fern fields were insectivores and omnivores, still operating in the survival mode that had carried them through the extinction. Then the palms arrived. Approximately 300,000 years after the impact, palm forests began establishing themselves across what is now central Colorado. With the palms came fruit. Calorie-dense, sugar-rich fruit capable of supporting larger body masses. Lyson's team found that mammalian body size tripled in direct correlation with the arrival of palm forests. Species in this interval reached approximately 25 kilograms, matching the same weight threshold above which no land animal had survived the extinction itself. In just 300,000 years, a span of time roughly equal to the entire existence of Homo sapiens as a species, mammals had recovered to the upper size limit of the original extinction survivors. By 700,000 years after the impact, the plant record at Coral Bluffs shows the arrival of legumes, bean family plants that fix nitrogen in soil, enriching it and enabling the growth of larger, more complex plant communities. And with those enriched ecosystems came even larger mammals. Lyson's team documented species exceeding 50 kilograms in this interval, animals the size of a modern wolf. The ecosystem was rebuilding from the soil up, and the mammals were tracking every stage of that reconstruction, growing larger in lockstep with the expanding food supply beneath them. Lyson published these findings in Science in October 2019. He described the relationship as direct and measurable. The recovery of mammalian communities was coupled, stage by stage, to the recovery of plant ecosystems. Each new plant community unlocked a new tier of mammalian body size and ecological diversity. It was not random. It was not chaotic. It was a sequence as orderly as a staircase, each step built on the one below. If you have made it this far into the video, you clearly want to understand how the deep past created the world you are living in right now. Subscribe now so you do not miss the next one, and I am not saying that to be polite. The algorithm needs you to click that button, or it assumes you are not interested and stops recommending this channel entirely. One click fixes that. While the recovery at Coral Bluffs was unfolding in Colorado, a parallel process was happening on every continent. The KPG extinction had not merely killed the dinosaurs. It had emptied every ecological niche that large animals had occupied for 165 million years. The large herbivore niche, the apex predator niche, the large marine predator niche, the aerial predator niche. All of them vacant simultaneously, for the first time since the beginning of the Triassic, over 200 million years ago. Stephen Brissatt, a paleontologist at the University of Edinburgh and author of The Rise and Reign of the Mammals, has called this period the greatest evolutionary experiment in mammalian history. Brissatt and his colleague Paige DiPolo published research examining the rate at which new mammal species appeared in the 10 million years following the KPG extinction. The speciation rate they documented was orders of magnitude faster than anything observed in the preceding 100 million years of mammalian evolution. Lineages that had been locked into narrow ecological roles for over 150 million years suddenly began diversifying into forms that bore no resemblance to their ancestors. I mean, think about that for a second. The same group of animals that had been confined to eating insects in underground burrows for longer than the entire lifespan of the Atlantic Ocean began producing descendants that swam, flew, galloped across open grasslands, and climbed to the tops of newly grown forests. Within 10 million years of the extinction, the ancestors of every modern mammalian order had appeared in the fossil record: primates, carnivores, cetaceans, the lineage that would eventually produce whales and dolphins, bats, rodents, hoofed mammals, all of them tracing their origins to the first explosive burst of diversification after the dinosaurs disappeared. The early Paleogene fossil record reads like a catalog of biological experimentation: mesonychids, hoofed predators with jaws strong enough to crush bone; Ambulocetus, an early whale ancestor that walked on 4 legs and hunted in shallow rivers before its descendants abandoned dry land entirely; Ichormecturus, one of the earliest known bats, already capable of powered flight within 10 million years of the extinction. Body plans that had never existed before were appearing, being tested against the environment, and either persisting or vanishing within spans of geological time that were, for mammals, unprecedentedly short. The part that keeps researchers awake is not the speed of the diversification, it is the realization that none of it could have happened if the dinosaurs had survived. For 165 million years, every ecological niche worth occupying was already filled by something larger and better established. The mammals had the genetic potential to diversify the entire time. What they lacked was the ecological space. The asteroid did not give mammals new abilities. It gave them an empty world. And they filled it in 10 million years with a diversity of forms that had taken the dinosaurs over 100 million years to achieve. If the mammals had stopped at raccoon-sized generalists eating ferns in post-impact rubble, this would be a very different story. They did not stop. The ceiling was gone, and within roughly 50 million years, those same marginal creatures produced the largest animal that has ever existed on this planet. The blue whale, weighing nearly 200 metric tons, heavier than the largest dinosaur that ever walked, descends from a small, four-legged, semi-aquatic mammal that lived in the aftermath of the extinction. The distance between a 100-gram burrowing insectivore and a 200-ton ocean predator is the distance that evolution traveled once the lock was removed. If you are not subscribed yet and you are still watching at this point, you already know this channel is for you. Subscribe now. The next video covers one of those Paleogene evolutionary experiments that went spectacularly wrong. The KPG event was not the first time this pattern played out. Lauren Salin, a paleobiologist at the University of Pennsylvania, published research in 2010 documenting what she called the Lilliput effect across multiple mass extinctions in Earth's history. After the end Permian extinction 252 million years ago, when more than 90% of all species disappeared in the most severe biological catastrophe ever recorded, a die-off so extreme that Earth's biodiversity took 10 million years to recover, the survivors were overwhelmingly small-bodied. After the end Triassic extinction roughly 201 million years ago, which cleared the ecological stage for the rise of the dinosaurs themselves, the same size-selective pattern appeared. In every documented mass extinction, the organisms that made it through were smaller, more generalist, and less dependent on complex ecological networks than the ones that perished. The Lilliput effect is not a statement about toughness or intelligence. It is a statement about dependency. Large animals occupy the top of food chains that required millions of years to assemble. They depend on stable climates, predictable seasons, abundant vegetation, functioning pollination networks, and prey populations large enough to sustain them across generations. When those systems collapse, the animals that depend on them collapse alongside them. Small animals, the ones sitting close to the bottom of the food chain, the ones that can eat whatever is available and breed fast enough to absorb catastrophic losses, persist through the disruption and emerge on the other side into an empty world. The pattern is consistent across 500 million years of geological evidence. In times of catastrophic environmental collapse, the large, the specialized, and the conspicuous die. The small, the flexible, and the hidden survive. And then the survivors expand into the vacuum, often becoming large and specialized themselves within a few million years, setting the stage for the next catastrophe to repeat the cycle all over again. Which raises a question that is uncomfortable precisely because the answer is obvious. Homo sapiens is the most ecologically dominant species on the planet. We are specialists in technology, infrastructure, and large-scale cooperation. We depend on supply chains that span oceans, energy grids that require continuous maintenance, agricultural monocultures that would fail within a single growing season without human intervention, and freshwater systems engineered to serve populations of millions. We weigh well above the 25-kilogram threshold that the KPG extinction enforced, with absolute consistency. We occupy the exact ecological position that has proven fatal in every mass extinction in the geological record. The mammals that survived 66 million years ago survived because they needed almost nothing. They could eat anything. They could shelter anywhere. They required no infrastructure, no supply chain, no coordination beyond the family unit. Their resilience was built entirely on simplicity. And the mechanisms that drive mass extinctions have not stopped operating. The geological processes that produce large igneous provinces like the Deccan Traps are driven by mantle plume activity that continues beneath active hotspots today. Stratospheric aerosol injection from major volcanic eruptions remains a documented climate-forcing mechanism that modern climate models take very seriously. NASA's Planetary Defense Coordination Office tracks thousands of near-Earth objects, some large enough to produce regional or global disruption events, precisely because the asteroid threat is not a historical curiosity. It is an ongoing statistical reality operating on timescales that human civilization has simply not existed long enough to witness in full. The geological record speaks with clarity on one point above all others. The species that survive catastrophes are not the ones at the top of the food chain. They are the ones at the bottom who can still function when the chain breaks. If that conclusion unsettles you, or if you disagree with it entirely, drop your perspective in the comments. I feature the strongest responses in future videos, and the debates in this community are genuinely worth reading. 66 million years ago, a creature the size of your fist crawled out of a burrow into a world blanketed in ash. The forests it had known were gone, and the enormous predators it had spent its entire evolutionary history avoiding had vanished with them. The sky was the color of slate, and the air tasted of sulfur and charcoal. That animal had no way of understanding that it was standing at the beginning of something. It was simply looking for a beetle larva to eat. But from that animal, and from thousands of others like it scattered across scorched continents, came everything that followed. The forests grew back. The mammals grew with them. They filled the oceans and the skies and the grasslands and the rivers. They developed hooves and fangs and echolocation and, eventually, hands capable of building instruments that could look back across 66 million years and find the crater that had started it all. The real question is not why small mammals survived when everything bigger died. The fossil record answers that question with detailed, measurable evidence. Small bodies, low caloric demands, generalist diets, burrowing habits, fast reproduction rates. The math is clear, and the data are consistent across every continent. The real question is, what happens when the next disruption arrives, and the same filter is applied to a planet whose dominant species has optimized itself for size, complexity, and total dependency on systems that only function when everything remains stable? The geological record has answered that question 5 times already, and every time the answer has been the same. If you want to see what nearly ended the human species itself, long after the dinosaurs were gone, the video on screen covers a catastrophe that left fewer than 10,000 breeding humans alive on the entire planet, a number small enough to fit inside a single football stadium. Click it now. And if you are not subscribed, this is the moment. Every single week, this channel goes into another chapter of this planet's real history, the chapters that textbooks skip and classrooms never reach. Subscribe so you do not miss it. I will see you in the next one.